Hey all, let's talk about a matrix as a function. So first things first, a definition of a matrix. So M by N, a matrix, so in other words I'm defining the word matrix here, is a box of numbers, M rows by N columns, that's rows by columns there. So that's going to have M times N numbers, M times N numbers in it. Those numbers are allowed to be any numbers. In examples, you'll probably see me using integers. Most books use integers, but they're really allowed to be any real numbers at all. At least in the beginning here. Maybe we'll get to more complicated things later. Okay. We can think of that box of numbers as either kind of primarily rows, right? Primarily rows like this, where we have row 1, row 2, on and on, down to row M. We said there are M rows, so there are M vectors across this thing. Or we could think about it in terms of columns. So that would be this picture where I've got column 1, column 2, and then we have N columns. Okay, so this is the idea of a matrix. It is this box of numbers. Now, the reason that a box of numbers is interesting to us is that we can think about it as a function. So an M by N matrix maps N vectors into M vectors. So the domain, right? And we're gonna have some conversations about domains and ranges and stuff. But for right now, let's just remember that the domain is the set of kind of available maps or available inputs. So that's Rn. And then we have a range of Rm. And if we want to discover kind of how this works, that's a M by N multiplied by a vector, which is an N by 1 matrix, you might recognize. This notation is just a little bit redundant. I could probably get away with either the vector hat or this N by 1. Both is overkill. You won't see me use both probably ever again, frankly. But for right now, I want to highlight that it is a vector, which we can think about as an N by 1 matrix. This multiplication will work so long as the inner numbers match, and the result will be M by 1. So that'll be a vector in Rm. Traditionally, B is used for the output there instead of Y for reasons, whatever. Okay, now, how does it actually act as a map? Well, there's a thought called the kind of row picture, right? Where I take an M by N matrix and apply it to an N by 1 vector. And the way I do that application, I lost some, there's some writing issues here. Okay, so let's fix them. So I have row 1, row 2, all the way down here. At the end here, I'm going to have row M, right? So I'm going to have all my rows, and then I'm multiplying by my vector x, and the way I'm going to do that is I'm going to take the dot product between x and each row. Now, this x is an N by 1 vector, and the rows each have N entries, so they are also N by 1 vectors, which means that these dot products are going to work, and they're going to result in a scalar. Each one results in one scalar, so I'll have M of them, which makes an M by 1 vector. Now the column picture is kind of the same thing but sideways. So the other way we could think about this action is we could say a M by N acts on an X vector that's N by 1 by considering the A as the columns, considering X as the scalars, and then considering the result as the linear combination of those column vectors using these scalars. So that would be x1 times the first column plus x2 times the second column, and kind of so forth until we get to the last one. That also is a vector in Rm because each column vector is a vector in Rm. Now, it maybe would be worth a second to convince yourself that these two give the exact same result. They do. Spend a second and figure out why. I don't want to give away everything to you, so we have our two pictures, right? Our row picture and our column picture. And then finally, I want to spend just a second on inverses. Because A is a function, And functions oftentimes have inverses. We're going to need to spend some more time on this later, but I just want to think about it for right now. So they only sometimes have inverses. I hope that makes sense. So the sometimes when they have inverses, one, they need to be square. They won't have inverses if they're not square. We could talk about why later, and we're going to have to talk about why later. But for right now, just assume that I'm correct. So I have a function that maps from Rn to Rn. An inverse would map backwards and undo it, right? So I would have this case where ax equals b is kind of the same information as x is a inverse b. That assumes that a inverse exists, right? If a inverse, like if that's even a reasonable idea. So my claim for right now is that you're going to need to have two things satisfied for that to work. One, it's going to have to be square, and two, the columns are going to have to be independent. If the columns aren't independent, then it won't be invertible. One way we could see that is we could think, okay, so if the columns are dependent, then we're going to look for a couple vectors that map to 0. One of those is going to be the 0 factor, right? I can see pretty clearly from both of these, well, maybe from this case, that if I put 0 in for the x's, the dot product is going to be 0 for each of these. We could see it from here too, in that if I put 0 in for the x's, all these are going to be 0 factors added together. So the 0 vector maps to the 0 vector. So I could probably revise this to be x1 is the 0 factor, right? And then x2, if there's any other vector that maps to the 0 vector, we're going to have a problem with invertibility, because then a inverse here wouldn't be a function, right? It would take 1 point to 2, and that's not a thing that functions are allowed to do. I hope that makes some sense. Like I said, inverses are not the point of today. We'll get to them later, but lots of students ask about inverses today because you have experience with functions. Okay, so things to remember: rows by columns, and they act on vectors using either the row picture or the column picture. These are relatively crucial. They give you the same result, but they're kind of different thoughts. So we want to have them both in our head. Carry on. Good luck.